Hey there, everybody. This is Mr. Sheeline. This video is going to cover the 2.4 notes, classifications of matter, which we've pretty much already done, but it's going to be classification of matter and physical chemical properties. And even though the last 2.3 note should have been classifications of matter, I like to put the title over here because, for the most part, this is how we classify how matter interacts with one another. What does so what's a chemical property versus a physical property? What is a chemical change versus a physical change? That kind of thing. It all goes into how we classify particular types of matter and how they relate to one another. So anyway, okay. So for the most part, or not for the most part, but you have everything filled in on these notes. But what I want to do is I want to make some, I want to really focus in on a number of points on here and highlight a lot of examples that are provided here and kind of help you navigate through these notes so you understand where to find what, because this will be the first set of notes for the most part that you've received that are filled out, that you don't have to fill out yourself. So as we can see here, properties of matter, so we've got physical and chemical properties listed here, and then we've got these pure substance and mixtures. So understand that these two relate to these guys, to this up here, but it's its own thing. So we'll come to this. I'll just understand that this is going to be its own little thing, though it is connected to physical properties and chemical properties as far as classifying matter goes and seeing how they interact with one another. So now physical, chemical, you can read their definitions there. But what I want to focus in on is the examples of the properties, because these are things you have to know. So physical properties, for the most part, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 different classifications of a physical property. Even there are some teachers that I know go to 12 or 13. Some scientists do as well. But for the most part, what you have to understand is that these physical properties, like the characteristics of these physical properties, are more or less how you see them. It's the density. It's how much stuff is there in a particular amount of space. It's the color, the melting and boiling points. When does it change? When does it change from a liquid to a solid? When does it change from a liquid to a gas to a solid? What are those points? Okay, because they can move between these. They can go from, think of water. Water can become a solid. Then it can become a liquid. It can then become a gas. And then if it's a gas, if you trap it, you can then make it into a liquid form again. Then you can make it into a solid again. So it doesn't change, and it doesn't change the properties of the water. The water's still water. It's just its state that's different. The shape of it, magnetism, is it attracted by a magnet or not? Viscosity. Viscosity is more or less how thick is it? Is it syrupy? Or is it super watered down? Does it flow at a high rate, or does it flow at a very low rate? Okay, that's viscosity. Conductivity. How well does it conduct electricity? Meaning, how well do electrons and energy move throughout this particular material? Luster. More or less, luster is what does it look like? Does it sparkle? Does it look like a metal? Or is it dull? Does it look like the tables you sit at? Do they not really have, is it a flat, does it look kind of flat, or does it look metallic? How bright is it? Volume and mass, that pretty much, is compiled in density, but how much space does it take up? And then how much matter does it have? So here are some examples, specific examples of physical properties. So specific example, you can read these yourself, but they're pretty good examples. Color of gold, that goes with color. Iron's attraction to magnets, that's magnetism. The thickness of honey is viscosity. A wire's ability to transfer electricity, that's conductivity. Okay. So then for chemical properties, again, you can read this definition on your own, but example of that is flammability and reactivity. Okay. Chemical properties are properties that cannot be observed without altering the identity of the substance. Okay, so as a specific example, it's flammability of clothing, iron's ability to rust, copper's ability to oxidize, to create that kind of, or like think of copper. So copper will create, that patina that's mentioned here. Well, I guess it is copper that we're talking about. Sorry, copper. So when water and more specifically oxygen bonds to copper, it goes from that classic, brownish, orangish kind of color, and also that luster. It has a really, glossy, shiny luster. It looks pleasing to look at. But when oxygen hits it, that oxygen binds to the copper, which then creates what's called copper oxide, and copper oxide is bluish in color. We don't get into why it is bluish in color, but understand that's what it turns into. That's why the Statue of Liberty is the color that it is, for the most part. It's that greenish bluish color. Okay, and it's that patina. It's that new bluish color, and also it's not so shiny anymore. It's kind of flat. It looks like a matte kind of paint. Almost think of it that way. Think of high gloss versus matte paint. Okay, and if you guys don't know what that is, look up MATTE paint. It's a particular finish of a paint that makes the paint look flatter. Light doesn't bounce off of it as much. But the chemical properties is how well does it burn, how well does it react, or if it reacts, when does it react, how often does it react, and change from one material to another. Okay. It also, we'll say that. Okay. Now these two are going to come back up on the backside. We're going to go from properties to chemical changes, physical changes. But I want to go into first pure substance versus mixtures. So now again, you can read the pure substance and the mixture definitions. So these are the definitions right here. What I want to focus in on is the subcategories of the pure substances and the two subcategories of mixtures. So for pure substance, there's nothing more pure than an element. So this is breaking something down into what a particular atom would be. Oh, there's another bell. Sorry. So and you'll hear that again another 5 minutes or so. But it's pure substance. We would consider pure substance to be an element or a compound. So the element would be, say, as an example, that is, you'd have, if you broke something down, if you broke water down, let's say you broke water down. You separated the hydrogen atoms from the oxygen atoms. The element that you'd be left with, a pure substance, would be that hydrogen. And if you were able to, gather up all that hydrogen into a little container, that pure substance, and if it was just hydrogen, you would have that pure substance of just hydrogen. But it also can be a compound. So an example of a compound, so here it says substance as chemically combined from two or more simpler substances and can be broken down into similar or simpler substances by a chemical reaction or change. Like that, an example of that would be, that would be water. Okay, that would be H2O. Okay, H2O is a compound. That is the molecule. Okay, what's another example? Another example would be, let me think here. Would be oxygen gas, which is O2. Okay, that's a compound. Okay, that's not an element, that's a compound, because an element is made of one atom. So here we have a compound that's oxygen gas. Oxygen gas is made up of two oxygen atoms. So here are two examples of what a compound would be. And those are what we call pure substances. Okay. Now mixtures are, as they sound, they are a mix of something. So we have homogeneous mixtures and we have heterogeneous mixtures. So homogeneous mixtures, for the most part, these are types of mixtures that in which substances are so evenly distributed it's difficult to separate them. Okay. Example of that would be right here. An example of that would be when you dissolve sugar in water. For the most part, it's anything that can dissolve into something else where you really can't really separate them. And the only way you could separate them is either through a chemical change or for a physical change. It's a homogeneous mixture. Okay, so a good example is sugar water. So if you had a glass of water next to a glass of sugar water, now of course it does depend upon how much sugar water and how much sugar is in there. But for the most part, if you allow that sugar to dissolve, you really can't tell the difference between them until you taste them. So that would be a homogeneous mixture, is that you can't separate, or at least your eyes can't separate the distinct materials that have been mixed together. Okay. A heterogeneous mixture, though, is a type of mixture in which the parts of the mixture are visibly different from one another. This would be a suspension. And a suspension is called a suspension for the most part because things sit on top of one another. They're kind of floating around independently of one another. And as it says here, separates into layers over time. So a good example of that would be mixing water with oil. That's a great example of a suspension because, eventually, as much as you shake it up, as much as you use a spoon to stir it and to make it one kind of material, eventually that you would notice that the oil and the water would separate, where the oil would sit on top and then the water sits on the bottom, just because water is a bit more dense than oil. Okay. And examples of that would be like, think of Italian dressing. So Italian dressing is made up of a little bit of water. It's made up of vinegar. It's made up of olive oil. Typically, it's made up. They put spices in there. They will put, maybe even some greens in there, other herbs, which would be part of the spices. But you understand what I'm saying. Like you could make a distinction. You could see the distinct different types of material floating around inside salad dressing, inside Italian dressing. Okay. Or like macaroni salad, or any pasta salad for that matter. You could say, oh, there's the macaroni, there's the pasta, there's the bell, there's the tomatoes, there's the cucumbers, the carrots, and you could pick them out, you could take them out, okay? And that's a heterogeneous mixture. If you can see the distinct different parts of the mixtures within the mixture, okay? So again, homogeneous. Okay, where, as we should see here, homo, meaning the same. Okay, homogeneous means that it, for the most part, looks like it's all the same thing. It's like sugar dissolved in water. Sugar, water, and water look pretty much the same. Heterogeneous mixture, this is where you have a mixture, but you can see the distinct materials inside of the mixture. So, like Italian dressing or macaroni salad, you can distinctly see them. Okay. All right, so if you still have questions over these two, make sure you ask me. Okay. And then just types of matter changes. So there's the physical and the chemical change. So this ties more directly with physical properties and chemical properties. So physical changes, you can read that definition, but look at these specific examples compared to, just the normal examples. Physical changes are like cutting, crumpling, tearing, smashing, crushing, dissolving, all states of matter changes. So this one right here is a big one. A lot of kids miss this one. That's going from not liquid. That's like going liquid to solid, solid to liquid. That's like solid to gas, okay, etc. Because a lot of us want to think immediately, well, if water's changing from a solid to a gas, if it's changing from a liquid to a solid, that has to be a chemical change. Something chemically is changing about the water, about H2O. But there isn't, okay? Water is water is water. The only way it's not water is if, let's say, you add heat to it, and an immense amount of heat to it, and let's say you add some sort of, I don't know, you could add an acid to it, and some of the water will separate, and the hydrogen will bond with one another. The oxygen will bond to some of the other hydrogens, and it'll bond with whatever other materials within the acid, and you'll have a lot of times you'll have hydrogen gas that's then emitted, but you're chemically changing in that case with adding acid to water, you're changing the chemical composition of the water. You don't change the chemical composition when you're changing from one state to another. So that's something really important to remember. And you can go through the specific examples on your own there. Now, a chemical change, now this one, I'll read this one. Change that alters the identity of the substance. It turns it into something completely different, something completely new. So this would be like burning, oxidizing, reacting, and generally reacting, because you can maybe say that there's some reaction somewhere up here, but reacting so much as this, wood burning, okay? Sorry, if you burn a log, you're not going to be able to take that ash and turn it back into a log. It just doesn't work like that, okay? Car rusting. Okay, that's one reason why a lot of people hate when they see car rusting, because there's really no point it's a point of no return. You have to either replace the panel on your car, or you've got to grind it to expose the better non-corroded material and then paint over it so it doesn't corrode. Okay, good example, like I mentioned, Statue of Liberty oxidizing, getting that green patina. Leaves turning color. Okay, once a leaf goes from green to orange, it can't go back. It is the chemical composition within the leaf has changed. Now the tree, potentially, if you were somehow to put it inside where it would be like spring conditions more or less, like the newer leaves, like the tree itself would slowly go back to green, but the leaves that already turned could not turn back. Okay. Cooking egg, so when you cook an egg, you can't undo that. That's pretty much done. Baking a cake, fruit or vegetable ripening, there's no point in which you can go back and reverse that. The chemical composition has changed. Okay, and these are important because, and this is something that I think for the most part, a lot of students will say, yeah, I get it. Physical changes are this, but there's sometimes where there are physical changes that students will mistake as being chemical changes. Not so much the other way around. It's a lot of students confuse physical changes with chemical changes. So make sure we understand both of these distinctly. And then here are 4 major signs that tell you that a chemical reaction, that a chemical change has occurred. So the first one, you have a change in color. So that's why, as a good idea, the leaves, or a good example, the leaves changing color on a tree. Okay, if you see something changing color, it's probably going to be a chemical change. Okay, I did have an example from last year that I'm blanking on, where it is a physical change where colors change. I guess as a simple example, think of if you're painting using watercolors. If you're painting on a canvas and you put a blue down and then you put a red down, it's clearly going to make a purple. So the question is that a chemical change or is that a physical change? Well, the answer should be that it's a physical change. It's not a chemical change, okay? Because you're not chemically changing the paint and you're not chemically changing you're not chemically changing the composition of the paper. What's happening is that you're combining 2 colors that once light hits, the light that bounces off of that just happens to be at a particular wavelength that emits every color but purple. So which is why you see purple. So which may be confusing you further, but understand that like for the most part you could wash the paper away, or you could wash the paper and for the most part the paper will go back to being paper. It'll be stained, of course, but eventually you can get that paper back to it being paper, like white, and then you would have a separation between the blue and the red ink, the blue and the red watercolors. Okay, and that's different from leaves on a tree, because leaves on a tree change, remember, from biology. They change because of the beta carotenes that are inside of the leaves. Remember, there's chlorophyll A, there's chlorophyll B, and then you have those beta carotenes that are inside, and pretty much the chlorophyll will say, yep, we're done here. We've got to start storing energy rather than, making it and using it up. And it switches from one kind of pigment, or it changes from one production of pigment to a different color, production of pigment, being those beta carotenes, which are more orange and red in color. Okay. Temperature, change in temperature. So if, like, hot hands are a good example. So those things when you're at football games or whatever kind of games that you're outside, during the winter, you kind of crush them up a little bit. You crush them up and all of a sudden, ooh, it feels nice and warm, That's an example. Another example I'll put down would be MREs. So specifically the flameless heat pack, FRHs, flameless ration, FRH. Flameless ration heater, that's what it's called. An FRH, I would look that up. If I were you, in MREs, some of them, not all of them, will have what's called FRHs, which is flameless ration heater, I believe, is what it stands for. It's very similar to hot hands, but for the most part, you put water in them, and the water reacts with a particular metal, and it boils the water, and you can heat up pretty much everything out in the middle of nowhere without a microwave and without fire. You can heat something up and eat something pretty warm. But that's a chemical change that's happening there. Okay, so change in temperature, or a production of gas. So if you mix vinegar and baking soda, you'll create CO2. So if you see a production of gas happening, it's 100%, especially with the production of gas, like for the most part, 100%, that is a chemical change. Now, of course, if you're boiling water and you're producing a gas, that's not changing the chemical composition of the water. That's just changing the state in which the water is currently in, i.e. being from a liquid to a gas. That's not the same thing. Here, it's where you have one distinct material mixing with another distinct material. In this case, acetate plus and I'm forgetting baking sodas. Sodium bicarbonate, sorry. So acetate plus sodium bicarbonate is going to give you CO2 as gas. And then the last, God bless, the last sign of a chemical reaction, a form of precipitate. What's a precipitate? It's a solid material made from a solution. So if you take milk and you add an acid to it, whether it's vinegar, if it's hydrochloric acid, if it's sulfuric acid, whatever it is, if you add it to it, you pretty much just make cottage cheese for the most part. Now, I don't recommend that you add hydrochloric acid to milk and then drink or eat it, because it won't be cottage cheese. It will be toxic, or at least it'll be somewhat toxic, and you don't want to do that. But anyway, but we should know, though, when you add milk to vinegar, the milk will begin to curd, and it'll separate, and you'll have these little chunks in there, and that's for the most part what cottage cheese is. If you don't believe me, go grab some milk, go grab some vinegar, take a little bit of milk, put it into a cup, take a little bit of vinegar, put it in your milk, and see what happens. And what would be happening there is you're forming a precipitate. Those little chunks would be the precipitate. Okay? So, okay. And then lastly, the law of conservation of matter. So this is super crazy important, because there's this law, and there's a law that's pretty much identical to this, and arguably it is the same identical law. There's a law of conservation of matter, and there's a law of conservation of energy. And what it states, what both of them pretty much state, is they states that matter, or energy, is neither created nor destroyed in any process. It only changes form. okay? And that's true from the sunlight that is beaming out of the sun, that travels to the plant, that then is converted into sugars, that is then eaten by a grasshopper, that is then eaten by a snake, or not a snake, but a mouse, which is then eaten by a snake, which is then eaten by an eagle, okay? All that matter, all that energy transfers from one thing to another, and more or less cycles through time. Okay, so if we don't end with the eagle then dies. It falls to the earth. It is then decomposed into soil. That soil then creates, that soil goes into the production, or part of the production, the growth of a plant. That plant then absorbs the sunlight. A grasshopper eats it, a mouse eats the grasshopper, a snake eats the mouse, so on and so on and so on. So it's the idea that, yes, you, sitting right there, are made of dinosaur poop and stardust. I know. Isn't it great? Doesn't it feel wonderful that the same materials that allowed the dinosaurs to walk on this earth millions and millions and millions of years ago are the same exact material that are making you, you? Think about that for a second, because that's a lot to take in. So the oxygen you are breathing didn't magically become oxygen out of nowhere. That oxygen has been circulating throughout this atmosphere, whether it was in as the form of O2 gas, whether it was in the form of a shell material from a crustacean, to the the oxygen found in water, whatever it was, the oxygen we breathe today, the nitrogen, the carbon, the nitrogen, the carbon, the oxygen that makes up your body is the same exact atoms that have been around since this earth was created, since this earth came to be. Okay, which again is a lot to take in. That's a lot to think of. Okay, and because again, matter can neither be created nor destroyed; it only changes form. Okay, so idea being is that total mass of reactants equals the total mass of products. Now it's a little bit of ways from what I was just explaining, but this is what we're talking, or I guess closer to the class. My idea is a bit more over-encompassing, and my idea is a bit more. I don't know the word you give it, but anyway. So to backtrack into, I did digress there a little bit, but total mass of reactants are equal to the total mass of products. So we get into more of this in Unit 3. We get way into it, in Unit 3 and 4 and 5. So it's like, how to give an example. A good example is photosynthesis. So think back to biology. So if you've got you've got CO2 plus H2O yields, and this is through photosynthesis. It's going to yield C6H12O6. So this is sugar plus 6O2. And this, I believe, that should be 6, yeah. And this should be 6. So the idea being is, if you count the total mass of the reactants equals the total mass of the products. Real quick, if you add, there's 6 carbon there, 6 carbon there, 12 oxygen, there's 6 oxygen, there's 12 oxygen there, 6, there should be 12 hydrogen, there's 12 hydrogen, and there's the other 6, so there's 12. So we should have more. Let's see. 6. Let me think about that for a second. So that's 12. That's where. So there's 12. That's it. So there's 12 oxygen here, 12 oxygen here, but then there's 6 oxygen here, 6 oxygen here. So in total on your reactant side here, you have 18. You'd have 18 oxygen atoms per se, and over here we have 18 oxygen atoms. Here's 6, 12, and then 6 plus 12 is 18. So it's the idea being is that, the oxygen just didn't stop being oxygen. It wasn't all of a sudden destroyed and new stuff was made. It was, no, it just, the oxygen's transferred to different places. Okay, the hydrogen was transferred to different places. The carbon was transferred to different places. So it's the same idea. Okay, and that is, for the most part, the notes. And I know that's pretty long for not really reading the notes, but that's it. If you still have questions about this, guys, make sure you ask me. If you don't really have any questions, then I'll see you in the next one.